Hello everyone and welcome to module 6 of DevOps. Today we are going to explore a new concept called Docker. Um, Before beginning or starting with Docker, I would like to know if you have any queries or doubts from the previous sessions. If you don't, we would be moving away with the new concept here. Alright, let's move ahead. What Docker has to offer here, we would be talking about what Docker has to offer, what virtual machines are, what are the differences between them, why do we use Docker, when do we use that. And after that we would be looking into the demonstrations of it, that is how to install it, how to work with Docker, what are the different features which are provided, what is Docker Hub, how do people deploy using Docker. And one biggest problem that Docker solves is environment replication, so how to bundle your dependencies with Docker. Okay, so here we have already seen a lot about virtual machines, right? Then why do we need a Docker or a technology that works on containerization rather than the virtual machines? Well, there are a few problems with virtual machines. The problems are that with a virtual machine, you replicate the OS files. All the operating system level files are all replicated. We have uh, replicated kernels. VMs would be having their own memory management, right? VMs have their own process management. Then resource sharing is not possible. Okay, or this happens to be a part of strict compartmentalization. That means we are very stringent about if the resource is allocated to this particular virtual machine, we won't be sharing it with someone else. So let's say out of my 16 GB RAM, I have shared 1 GB RAM to a virtual machine. So virtual machine is capable of using all of that, and it will not be sharing any even a bit of memory from its own memory place to another virtual machine's memory place. Well, that's good in a way. So when we say that we want exclusive holding of the resources, virtual machines are a good solution there. But the problems start to uh, like generate from replication of the operating system files, replication of the memory management and process management stuff. So when we're talking of running virtual machines on a base operating system or even on top of a hypervisor, in that case, as many virtual machines we create, we are replicating all those things, or there is a redundancy that is happening. So let's say if I was able to take all these redundancies in one single place, okay, so you already know the differences between type 1 and type 2 kind of hypervisors, right? Bare metal hypervisors and the hosted hypervisors. In hosted hypervisors, we waste resources because operating system is taking up the resources. Eventually, if we say that, okay, I would be needing an operating system, maybe it is a bare metal hypervisor or just a base operating system or on type 2 hypervisors, it's okay that we have a kernel, we have some operating system files, we have its own process management and memory management stuff running. So if I already have all these things, why do I need them to be replicated at virtual machine levels? Another is uh, about virtual machines, we have processes running, right, with all other processes. So what I meant to say here is, let's say a virtual machine, you're spilling a virtual machine, and the virtual machine is given 1 GB of RAM and 1 core CPU power. You want to run a web server on it. How much share do you think would the web server be getting? Because the virtual machine has to take care of its own memory management and process management stuff, it would be running 60, 70 different processes in the background, which would be acting as a support system for your web server process. And actually the web server process would be spinning up just one single thread, so one more process is supposed to be executing. But let's say I was having a capability of removing all these background processes somewhere and execute only web server process because I'm interested in only executing web server process. If that could be done, that would be really nice, right? Because we are saving on a lot many resources which are actually redundant. So Docker provides us with a containerization technology. What Docker says is that you don't need to replicate all of these things. But it comes with its own pains. Docker says that strict compartmentalization is not possible here because we are not going to give some exclusive share of resources. So it would be just another process running on my machine. Currently, if my machine is running 100 processes and I want another web server to be running inside Docker, it would be 101st process that is running now. And like in case of any of the operating systems, if I show you my task manager, each one of these processes which is available here on my machine, each one of them would be having capabilities of using all the amount of RAM that I have, right? They don't use it, that's their own good nature. But if a process decides to eat up the RAM, maybe 4 GB, 5 GB, 8 GB, it could do that. So virtually every process has got 12 GB RAM on my machine because my RAM capacity is 12 GB. Every machine has got access to 4 different CPU threads because the machine is having that capacity. Okay, so we are optimistic about resource allocation. We think that if we give the complete control of the resources to the processes themselves rather than splitting them up in virtual machines, it would be more beneficial. We would be able to pack in more processes in one single machine rather than splitting them up one per core in virtual machines. Again, the benefit would be, since Docker is a containerization technology where what are containers rather? Containers are namespaces. Okay, it's a very simple definition for them. In programming language, we have seen classes, right? If I want to access an attribute inside a class, I would say class name dot attribute name. If I have to access something inside a package, I would say package name dot module name dot class name dot attribute, whatever it is. Okay, so the namespaces define where that particular attribute lies. And if there are similar attributes between two classes, there is class A and class B having attribute name to it. If I call A dot name, it is going to hold a different value. If I call B dot name, it's going to hold a different value, right? Similarly, in process execution, we create a namespace, and inside that namespace, the process would allocate all its dependencies, all its memory or heap structures, anything that it requires, so that other process cannot step up or step into the zones where the first process is running. Okay, so if you are able to do so for all the dependencies, let's say with a web server, what do we need? We need code, we need configuration files, we need some custom configurations to be set up, right? And all of these things, if we are able to move along with the process itself, okay, I'm not just talking of one single process that is using resources from the operating system. I'm talking about a process which is having all its baggage packed into itself, everything that it would ever require. If you could bundle it up along with the file systems, along with the memory management thing, along with any of the dependencies that it needs to run in one single package, that package is going to be called a container. Okay, so containers are having their own namespaces. Process does not execute beyond that. Moreover, no other process would be able to get inside of the container unless and until it is having super user access. Well, that's what is a security hole with Docker, but let's not go there for now. We'll discuss in some coming minutes. So if I want to run a web server, or rather I want to deploy a code, so code deployment requires some machines. So currently what we have done is, until now, we have created web servers, right? We have deployed the code on the web servers using Jenkins. Fine, but for deploying code, I need a virtual machine. One machine per web server, that's what the rule is. And I cannot install anything else on top of that virtual machine, right? So if I happen to provision that virtual machine for a web server, I cannot run a database on it. If I provision it for application A, I cannot run application B on it, right? And that's for the good reason. Rather, people have learned from mistakes and they say that running one service per machine is a very, very good strategy. So we don't want to cross them on that concept. Well, that's good, but with highly increased capacity systems, we are wasting a lot of resources. If my system is having 2 GB of RAM and I'm not able to use all of it, if I'm getting 4 core CPU power and I'm using only 2 or 3% of it, I'm wasting rest of the resources and I'm wasting money on it, right? So if Amazon gives me a 2 GB section or subslice from its RAM, it is costing me maybe X money, and Amazon would be charging you for 2 GB. It wouldn't charge you for the percentage of RAM that you use, right? For Docker, it becomes a bit different environment altogether. So Docker packs all your dependencies using union file systems, dependency packaging. Okay, we could easily replicate the environments. How do we do that? Since I say that every process would be packaging all its dependencies along with all its environmental parameters, right? That is also included. So if I want to run that process onto any other machine, I don't have to worry about the environment replication. I could create a process on CentOS, run it on Ubuntu. I could create it on Ubuntu. I could run it on Windows. No matter what the operating system is, we should be able to port it, right? And since the environment is bundled up with the process itself, we don't worry about the environment. If I configure it once on production, if my developer needs the production copy of it, I can simply pass on the Docker container to him. Then replicating environments, yeah, dependency packaging is one. It is based on union file system. Okay, so it's based on union file systems that would help us in creating file systems as layers. So consider that all your common part. So Docker is a technology that is based on kernel, very specifically on LXCs, Linux containers. So Linux containers see their base or inception after the Solaris era, where Solaris were running their own containers, and they had capabilities of running multiple operating system copies on one single machine. So you might know about multi-boot systems where we have Windows and Linux installed on one single box, but we don't run both of them at once, right? Either Windows is up or Linux is up. In case of Solaris, you were able to run multiple copies in parallel. Okay, so that was a good idea. So that's where the containers found the basis or of concepts, and they started their own line of development. Linux provides its own containerization technology, which is a bit tricky to use at times for a person if he's new to system administration. So Docker is a company that took up this idea, created a wrapper around it so that it becomes more easier to interact with. And this is where the Docker tool formed, and we are using it now. The basis of it is eventually Linux containers. So if you know how to interact with Linux containers directly, you don't have to go with Docker. Okay, but since Docker provides you a nice, easy way to interact with Linux containers, you would be using it. AUFS is the default file system that is supported by Docker. And I was talking of layers. Okay. So kernel is a redundant system. Every machine has it, right? If every machine has it, is it a possibility that I take away that layer from the virtual machines and store it somewhere else so that all the virtual machines can interact with the same kernel? If each of the virtual machine in a cluster is having same operating system files, I'm not worried about the different dependencies that the process would be bringing in. I'm just concerned about the base operating system. If all of these files are same, across all the virtual machines, can we take out the common part and keep it at one single position, at one single location, and whenever someone needs it, they can take it over from there. And eventually, they would not be messing up with the file system or the kernel because they are uh, accessing their own namespace. Okay, so it's just like a class. So you have a class, you create different instances out of it, and different instances would be able to use different class attributes according to their will. They will never step onto each other's foot, right? Similarly with Docker. So Docker is providing you with a way of bundling up the stuff. At the same time, it is highly portable. Any system that supports a kernel would be able to run Docker natively. For running Docker, all you need is Docker engine. Just like in case of Java, if you have a Java interpreter running on your machine, you could run Java code there. Very simple, right? The code can be ported to any of these machines. The requirement is Java interpreter should be present there. Similarly with Docker, you could port the Docker files or Docker images onto any of the machines provided that it has got Docker engine running. And Docker engine runs on kernel. So if your machine is having a kernel, you should be able to run Docker on it. About Windows, we don't have direct Docker support on Windows. Rather than that, Windows has got its own technology called Packer that it uses. For Docker to run on Windows, you need to first have a Linux machine running, a virtual Linux machine, which would be providing you with a kernel support, and on top of that kernel, you are running Docker instance. So eventually, you need a kernel somewhere. All right. Another use case of Docker is that these days, since we don't want to waste money on resources that we don't use and make optimum utilization of the resources. I told you that the VMs is a pessimistic kind of resource allocation, whereas Docker is the optimistic kind of resource allocation. So in the systems like Kubernetes, or there is another one called Docker Swarm. So these tools provide you with an abstraction that helps you to consider your complete infrastructure as one single resource. So what I mean is, let's say you have got 1,000 machines. Each of your machine is having 2 GB RAM, right? Very simple, simple commodity boxes, and maybe one core CPU power. So how much resources do you hold actually? Each one of the nodes would be having 2 GB RAM and one core CPU power. If you look at it at one single resource pool, then in that case you have got almost 2000 GB of RAM and 2000 x computation and 1000 x computation power, right? So if you have those many resources and you don't want to worry about where the application runs, since you are using Docker, anywhere your machine application runs, you don't have to worry about the servers in that, because your process would already be bundled up along with all its dependencies. So if the process is running as a web server on any machine it runs, it is going to run as a web server. And moreover, since you don't need multiple kernels to take care of it, you could run multiple Docker instances on one single machine. Make sense? So in case of Google, these people are using Kubernetes as their internal resource pool manager. So what they do is they are running containers, and every container would be different. Maybe there are 6, 7 containers running on one single machine, which relate to different applications. So one of the containers might be for Gmail, another container would be for Google search, yet another would be for maybe Google Drive. If you kill one of the containers, Docker would be happy to spin it up on some another machine if you want to. Okay, so there is no affinity between the machines now. We are more concerned about where the process executes, not where. We are only concerned about if the process executes or not. Where it executes is none of our business. It's handled by one of these things, either Kubernetes or Docker Swarm. Okay, so that is the background of it. How do we put it to use? Let's install it and see what it brings for us as a DevOps person. So I would be installing Docker. Of course, for that I need kernel. For requiring kernel, I need a virtual machine. So again, I need to spin up a DNS, and I would be spinning up another machine, call it as Docker. Remember that Docker server requires 64-bit Linux installations, and it is very critical about which operating system it supports. So current versions of Docker would support Ubuntu 64-bit 14.04. Any operating system before that will not support Docker. Okay. So make sure that you have the latest release, Ubuntu 14.04, the template that you created. Similarly, you'll have to create a template called Ubuntu 14.04 64-bit, not 32-bit. And this is the only machine that we need as 64-bit in our complete architecture. Now again, there are a few terms in Docker. Um, in Docker, you would be talking about Docker images, Docker containers, okay, and Docker Hub. We could have two images sorry, not two images, two containers talking to one another. We could have containers sharing ports outside the parent machine as well, so that we could be able to access the processes that are running inside the container. You could also commit the changes that you have done inside the container. So to compare it with what you already know, is images could be considered as classes. Containers would be the running instances of the images, which are which you could say are instances, or rather objects. Okay, anything that is present inside a container, you could commit it back to the image if you want to. So it is a kind of version control system for your operating system itself. It does not maintain a history of it, rather. Okay, so it's not exactly a version control systems, but you could track the changes, create different versions of it, and then share it with other people. So it's actually beneficial when it comes to deployments. Deployments with Docker is really fast way to do deployments, so that you don't have to worry about the packaging of code, packaging of any dependencies, or along with it running the web servers inside your machines. You could bundle it up as one single Docker image and run that image on any number of machines you want to run. Okay, eventually it is going to be a container that is spinning up there. So we have this Docker machine created. I'm starting it. There are a few steps. I'm following these steps from the Docker website itself. If you want to Google it, you could Google install Docker Ubuntu. It would bring up a nice page here. So we are following the rules for Ubuntu Trusty 14.04 LTS 64-bit. Okay. There are multiple steps, but all of these boils down to only two parts. Two parts would be to add a source key, okay, and update your repositories. After then that, everything is the general thing, that whatever steps you generally follow in installing the software, apt-get update and apt-get install Docker engine is what is required. Okay, but adding the key is the important part here, and adding the source list is important. Point number 3 and point number 4. Everything else you could skip if you don't want to read it. Okay, if you are using some operating systems which are older, then you'll have to take care of the prerequisites, but for Ubuntu 14.04 there is no prerequisite there. So let me bring up this machine. Docker is already running. uh, okay, I would connect to this machine from my SSH client. D6.64. Okay, so let's add the key now. I'm adding the key for verification purposes here. Then we would be needing to add a source list. Just add in the key. Next thing is we are going to create a source list for Docker in apt-get. So the file is going to be at etc apt sources.list.d, which is a directory, and create a new file called docker.list. Add a line which says that all your repositories would be available at this particular URL. Save it. So the other things are pretty much same. Apt-get update and apt-get purge. Well, I'm using purge for getting rid of any of these packages that may be present on this machine, which actually are not, but it's a good way uh, to go along with the things. When you install a new package, you need to make sure that the previous packages are scrubbed off the machine. Okay, so I'm deleting any of these which might be available on this box and install a fresh copy of Docker. Apt-get install -y Docker engine. Okay, so I've merged three commands in one, and this should take care of installing Docker for us. Apt-get purge should be automated. Right, done. Step number one, adding key. Step number two, adding a source list. Step number three, install Docker. So there are more than 15 steps which are present here in the documentation, but I'm using the only ones which are required. Now here we need to give it some time for finishing up with the commands. It might take a few minutes. It seems to have been stuck. I'll repeat it. Apt install Docker engine. Okay. So here we need some more time for this to finish. It will take a few minutes for downloading and installing Docker. So we are almost there. Alright, so we are done with installing Docker. If that worked successfully, you could type in the command called Docker and see if Docker provides you with a list of subcommands. So the interface that these Docker people have put across or put around LXCs is very simple or easy to read and understand. So you could go through all these commands and figure out what it does, and you could choose any one of these according to your requirements. Okay, so I'll navigate you through a few of these commands. Very first thing that you would be talking is about Docker.info. Docker.info says that how many images are present, how many containers are running currently, what are your system properties, very few detailing about it. Okay, but the important part comes here, the first two lines: zero containers, zero images. So we don't have any images. Okay, so for creating any of the process first, we need a base, or consider this to be a virtual machine, but rest of the underlying technology which is redundant is completely scrubbed off. It would be taken care by Docker itself. So very first I need an operating system, right? So what I'll do is I would rather use an operating system which is minimum. So there is a minimum version of Linux present here. It is called BZBox. It is hardly 1.13 MBs or so in size instead of 600 700 MB. So what I'll do is I'll quickly download that part. Just like in case of Puppet, we have seen that Puppet holds all of its modules at Puppet Forge. Chef holds all of its modules at the supermarket. Similarly, any of the base images that you would be needing for spinning up your Docker containers would be present at hub.docker.com. So at hub.docker.com, we would be downloading the images. So I need an image for BZBox. First, we'll see a few examples with BusyBox. Then we'll be installing our own web server and installing that web server using the Ubuntu image. We are searching for BusyBox. There it is. So BusyBox official image. Click on it. It would give you some information about it. So, like I said, there are different versions. It acts as a basic version control system for your operating system. So this operating system here, which is BusyBox, has got multiple versions or tags to it. The latest one is 1.24, and there are multiples that you could use. So here I'm going to use this image by this command, docker pull busybox. So let's do that thing. Docker pull busybox would download that image for me. And since the kernel is already present, the basic process management and memory management things are already present here on the base machine. We don't need to pull in those layers. Only the different layers or the layers that would cause a difference would be downloaded. Okay, so it has downloaded it pretty fast. Let me show you the images. You could check the images by typing docker docker images, would show you the images, and it is hardly 1.113 MB in size. Okay, that's a virtual size, of course, because if you talk of just BusyBox, it needs a kernel to run, and kernel never packs itself in 1.113 MBs. Right, so 1.113 MBs is just difference part or the delta that you need to download from the Docker Hub. And how do I use it? Let's say very first thing that anyone would do with Docker is to simply try out a command. The containers that you are running, you could interact with those containers. You could fire commands on those containers. You could run scripts on those containers. So I'm trying to run the container from the base image. So base image, consider that to be my class. I'm going to create an instance of it. The running instance is going to be called as container because it contains all the dependencies along with it. The command is docker run from the base image busybox. Okay, and I'm going to fire a command on it. Simply echo hello world. Okay, so after your image name, anything that you write is going to be passed as a command to that particular container. So what would happen if we try to execute echo command on the container? We would be getting hello world back. Okay, so what happened in the background? The container was initialized from the image. The container started itself. We fired a command. Container executed the command, and as soon as the work of that container was done, the container stopped. So the resources are not still being utilized. The resources are released in the free pool again. That's why we use optimistic resource allocation here, because we trust the processes that they wouldn't be using more than what they actually need. How do I check the containers? The command is docker ps. There are multiple options to ps as well. Okay, we are aware of ps aux command, right, to see all the processes on our computer. So docker ps minus a will give a list of all the containers which were running in my system as well, which are and which were running. Docker ps would give me the list of only the currently executing containers which are live. Here it is saying that the container with some ID, which is identification number for that container, unique identification number rather, using the image busybox, has executed a command that starts with bin echo hello something, right? It was created 55 seconds ago. It exited normally with status code 0. From bash we know that 0 means success 55 seconds ago. So all these things, that starting a container, running a command, shutting down the container, releasing all the resources back to the pool, happened within 1 second, not even 1 second, right? Created 55 seconds ago and killed 55 seconds ago. Are there any ports that have been exposed? No. Are there any other resources that were being used? No. What is the name of that container? It says distracted Saha. So container is given two identifications. One is the container ID, that is going to be unique. Then another one is the name again, which is again going to be unique, but since it is a name, it is easily understandable and we can remember it as humans. Remembering a hash could be a tough thing. Okay, so this name is randomly generated from the pool that this Docker engine is already having. So it would generate very random names. So if I run this container again one more time, I would be getting a new container with a new name. So let me show it to you. Docker ps minus a. So then there is a new container with new ID and new name. It's suspicious Austin. All right. That is a simple command. But if you want to run a web server inside of it, well, we could run a web server as well, but you need to make sure that the web server always executes in the foreground rather than in the background. Okay, so if your web server runs in the background, it will not block the terminal, and if it doesn't block the terminal, your Docker container would just start and then stop itself. We'll see of these examples in a few minutes, but before that, let me show you the different operations that you could do on that container. Okay, the container started, it executed a command, it stopped. If I want to start it again, I can again start it. So I could say Docker start the container. The container name is suspicious Austin. So I could start it. Now let's check the status of it. Docker ps minus a. It says that the container was started a minute ago, created a minute ago, but it exited 6 seconds ago, just now when we fired the command and we are talking. Okay, so it is not blocking the container because the command that was fired was simply hello world. Okay, we could attach to the running container if it is already running. I'll show you that, but we first need a container that is running for that case. So for that, what I'll do is I will simply create a small shell script, and we will see that it runs. So this shell script is going to simply type Docker on screen, and we'll make it in infinite loop so that it acts as a daemon. So here I'm writing a command where my sample job is a variable, and if I want to fire a command and get its output inside a variable, I would have to run it like this, right? From the previous class that we have done on bash, the command is docker run. I want to run what? A container from image called busybox. Now this time I want to run it in the background as a daemon, so I would say -d. Okay, the command that I want to fire is bin sh. Bin bash doesn't is actually not supported in busybox. And the code that I want to write, I'm not creating a file, I'm rather passing the code directly to the sh as a raw code which is provided by -c. We'll say while true, which is an infinite loop, multiple lines on same line here in bash separated by semicolons. Do echo docker, or we could even write something like this: let count equals to 0. While true, do echo docker count, right? Then we say let count equals to count plus 1. Nothing fancy, right? And sleep 1 for making it delay the results, and then the end of the loop, which is done. Will that script work? Let's see. So docker run was executed, and whatever the pointer of that particular command is, it's stored in the variable called sample job. If I want to check the logs of docker, then I would be checking it like this: docker logs, the container name, okay, which is stored in the sample job currently. So it says in sample job, sorry, it is sample job. So that's working, but our counter doesn't seem to be coming up. There might be some problem with the code that we wrote. Echo docker dollar count should have worked, right? Okay, let me cross check the code again. That's not a problem. The only stuff that you need to remember here is that the docker container is running in the background. Okay, and we are getting logs in incremental fashion. Every second this result is going to be increased in length. If I want to stop it, since it is running in the background, if I want to stop it, I could do a thing like this: docker stop the job, which would stop that sample job for me. Another way to do it is to call on the container name directly. So the job stopped, and let me stop another instance of it. Docker ps minus a. It says one of the instances exited by 137. We killed it, rather. It didn't exit cleanly. Another one is up for last 2 minutes. I want to shut it down. So for shutting it down, I need either the identification number or I need the name. So I would say docker stop the name. That should stop the another instance. Okay, so that is now stopped. If you check the status of it, docker ps minus a would give you the status. It says it exited with the same uh, code, exit code 137, which means it was not a clean exit. We have terminated that prematurely. If you want to clean all these containers, since these are containers and they are based on union file system, they would be having their own files created. Okay, and if anything modified inside that container, it would be storing it for your usage later on. Even if the container killed itself and it's not running anymore, the files are kept. Okay, files are kept for debugging purposes. If you want to store those files, you could store them um, or commit them back to the image if you want to make it a part of the image. I'll show you how, but we'll do that in the case of Apache when we set all these things up with Ubuntu images. But if you want to clean this up, I don't want all these files present on my disk, I want to clean it up. In that case, I would be cleaning it up using the command docker rm remove, and remove what? So the identification. So this time I'm using id as identification, that remove that container. Docker ps minus a should give you list of 3 instead of 4. But if you want to kill all of these at once, then we do something like this. Docker rm. So I need just the first column, right? The IDs. So let's fire another command. Docker ps minus a, just give me the IDs of it. Okay. And out on this result of docker ps minus a minus q, we would be firing a command docker rm. So docker rm would be executed repeatedly on any number of IDs that are present here in these rows. All killed. Docker ps minus a is now empty. Okay, so you cannot delete a container when it's running. So there are no ill effects of docker ps minus a minus q with docker rm. If your container is already running, you cannot kill it. You'll have to first stop it. So if you run this command on all of these different images which are present, it is actually ensured that any of the running images or running containers are not killed. Okay, let's talk about the committing of the images back. If I make some changes inside the busy box, let's run another one. Docker run. Now this time I want to provide my own name to it. So I would say name hyphen hyphen name, and the name would be anything. Call it alpha. And instead of firing a command, I want a terminal. I want an interactive terminal where I should be able to fire the commands on my own. Okay, might be I want to fire multiple commands. I want to configure the container, and I also want to show you how it is committed back to the images. So I'm using a command called docker run. I'm providing my own name to the container. I'm using it as a terminal. So minus t is for terminal, minus I is for interactive terminal. You could merge them together into minus ti from the image called busybox. Okay, and the terminal that I need is bin bash. Sorry, bin sh. Bash is not supported. So on screen you see a slash terminal. So this terminal belongs to busybox. The number of folders, the number of utilities that are present inside busybox are very, very limited. Okay, even in Etsy you don't have many utilities installed, so it's a bare minimum operating system. So what I'll do is I'll quickly create a file here in temp. Currently it is empty, so we'll create a file called test. So there's this file test alpha. What I want to show you is whenever you kill the container, the files are still persistent. till the time you clean the container from your records. Otherwise, if I want the changes to be committed back to the image, and anytime later when someone creates a container from the image, he should be getting all those files intact. Just like we created the virtual machine, right? We created a virtual machine, the base one, then we installed some packages on top of it, and then we are cloning it. So every machine you clone, you have the pre-installed package, pre-installed network interface, all configured right to use. Similarly with Docker, if you want the changes committed back to the images so that other people who are running the containers from it should get the changes, then you commit them back. So I've created a test alpha file here. Okay, and how do I get out of this box? Simply hit exit and you should be leaving the terminal. What happens to the image now? What happens to the container, status of container? It says it exited cleanly 7 seconds back. So we were blocking that container from killing itself because we were working in the foreground, not in the background. And the name of this container is alpha. It's not any of the random name that the Docker engine is giving to it. If I want to start that container again, Docker start alpha. Okay, so it says that the container is up now and it would be running without our own help. The reason why it is because in the previous example, when we started that container, we started that container in a daemon mode, right, with the infinite script. That's the reason when it executed for indefinite time in the background. In the very first example, it didn't do so. The reason for that is we didn't block the terminal. In the latest example here, I blocked the terminal by passing -t-i. So when I execute the docker start command again, the container would be running, but no one is rather working on it. Okay, so the container status is still blocked. To attach to that container which is running, so the command is again a different command. I am not typing ps -a. I'm just hitting ps, which gives me a list of currently executing containers. If I want to connect to this container, I would be using docker attach to the container. So container name is alpha. I get a root to it. Okay, is a file present there? Cd to /temp and check it. Yes, the file is present. So I'm exiting from this container. So the container is no longer running. Okay, and we have checked that the file persists between the two container instances, and we could rerun the same instance again without creating it from the base image. If I want to commit it back, so I could do something like this: docker commit, and the image that you want to commit, alpha, to the new image name. Either you want to replace the existing image, so I would be simply writing bzbox. But if I want to create a new image with a new tag, I can give a completely new name to it, or simply if I want to commit it using a different tag, so I could create a tag. The syntax is image name colon tag name. If you don't provide a tag, the tag would be latest. Okay, so it is latest. This is what the tag name is going to be. So I'm giving a new name to it. I would say bzbox alpha should be used for committing it back. So it has committed it. If you check Docker images, you'd be having two images now. One is BusyBox latest that we have downloaded. Another one is BusyBox alpha, which has got a few changes to it, and the virtual size is a bit different. Okay, so that is in incremental fashion. If you want to push this BusyBox back to the hub, in that case, you'll have to create an account there, log in into hub, and then pull the image. And now if I want to push it back for storing it, of course, that's a paid feature. You could do it like this: docker push. We used pull for pulling down the image. We use push for pushing it back. So busybox colon alpha. So this is when you push the images back. You can also see the difference between the image and the container. Okay, so for that we could check Docker. Let me see, it's Docker diff, I guess. Uh, yeah, so that's Docker diff. Docker diff on alpha. So what changed in alpha? Alpha is the name of the container. So we logged into alpha, that made us create this .ash underscore history automatically. Okay, so that file creates automatically. Then we changed the temp directory and have added a file called test alpha into it. Okay, so we will have complete list of changes that have that the container has gone through from its time it started till the end time. If you want to check the history of the particular image, you could type commands like this: docker history and the image name. So the image name is, in our case, bzbox colon latest. We will check the history of both of them. So it says there is no history present here, not much. Okay, the base image was present in, and after that we simply fired the command sh on it and added a small file there. So that was the base images thing. What about our image? Busybox alpha. Similarly, nothing much. We have created it from the base image, right? We fired the command here, base image, have added a small file of 86 bytes, and the previous two steps are from the base image itself. So there are three layers present. The base image contains two layers, and the new image that we have created has got one more layer added to it. Okay, so if someone else tries to use our image and works on it, in that case he would be adding his own small layer to it, and all of these layers would be sitting one on top of each other. Okay, so if someone uses the base image again from busybox itself, of course, so in that case he will not be duplicating the code which we already have. It would try to match the layers which are already present on the system, and if the layers are already present, it would be using it from this AUFS file structure. That's where the union file structures really shine up. Let's see a few more things about it, like installing the packages, running the web servers. How do we import an image? How do we uh, export the image for portability purposes? Okay, so for that I need another instance here. I'll create a web server and rather show you how do we export the ports so that we can deploy the code inside of it. Okay, and then serve our users with that service. For removing the image, the command is RMI instead of RM. RM is for removing containers. RMI is for removing the images. Very first, let's get a list of the images. Docker images would give us a list. I don't need the busybox alpha for now, so what I'll do is I would simply remove it. Docker RMI busybox, and very specifically remove alpha. So that was removed, and now I have just one single image. If I want the image for Ubuntu because I want to install Apache, so let's go back to Docker Hub and try to search it here. If you don't want to go to Docker Hub, there is another nice command that you could type: Docker search Ubuntu. It would search Docker Hub and it would give you a list of all the images that are present. You could use the one that is suitable for you. It says Ubuntu is the image name. Ubuntu is a Debian-based Linux operating system, blah blah blah. Have got multiple stars. People have used it a lot. It's official, so I would be using it. So the command is going to be docker pull, the image name is Ubuntu, and the tag that you want to pull is latest. Okay, allow it a few minutes for downloading. It wouldn't take long, but you would be amazed by the size that it actually tries to download. Just 65 MBs. Okay, it's not 600 or 700 MBs, not even GBs. It's only 65 MB file that is going to be downloaded as a base layer. Okay, so we have just downloaded the Ubuntu image. So what I'll do is I'll log in into Ubuntu, install Apache, and I'll show you how to get the code there. Very first, we are going to run the image. Docker images, what is the image name? It is Ubuntu latest. Okay, so Docker, run a container, name it Apache, get a terminal for me for firing the commands, use it from an image called Ubuntu latest. Okay, and fire a command bin bash. Now we have bin bash present. Okay, we don't need bin sh this time. Hit enter. You've got a console which says root at the rate this particular ID. The ID is the container specific ID. And let's install Apache. It's very simple, right? Apt-get update and apt-get install Apache. Okay, so what we have done now is installed Apache here. If you want to check, what I'll do is I'll simply duplicate a session. We'll connect to the Docker computer again. I will not lose the console, okay, so that we get to know what the container is doing. Docker ps minus a should give you the container that we have started. It's container Apache. It says that it is still up since last 3 minutes, and we have simply installed Apache inside of it. So what is the differences? What are the differences there? So we would say Docker diff on Apache should give us the diffs of that particular container. So many files were changed, so many directories were added, a lot of things happened since we started our Docker container. Okay, just like in case of a version control system. Okay, so that container is already running. So how do we make sure that the code moves there? There are three ways of getting the code in there. First one is to check out the code directly from a version control system. Okay, so I would be installing Git, and then I'll do git clone and get the code there. Another way is to use a Docker file for copying the code from one location on your host machine to the another location inside this particular Docker container. Okay, and the third one is to use a volume, okay, or a disk volume. So that is passed by -v as a parameter. So the command would be, of course, you would be firing this command outside the Docker container, but I'll show you here. It is docker run, whatever your image name is. Okay, if you want to get a terminal, get a terminal. If you want a volume to be copied, or rather not copied, I would say it is mounted from your host machine inside the Docker container, you would be doing something like this: v the path, okay, on the host machine, to the path inside the container. That's how you'd be moving the code. These are the three ways that you'd be doing. I'll show you quickly how to write a simple Docker file, and using that Docker file you could configure the Docker instances. So you don't even have to configure the Docker instances all by yourself. You don't have to fire these commands whatever we are doing here, but we are doing it just for the sake of manually doing things so that you get to know more about it. I've installed Apache here. What is the status of the service? Service Apache 2 status, it is says it's not running, so I'll rather start it. Apache 2 start. So it is running now. But how do I export it? How do I make people to access this container? This container is running inside my host machine, right? So I need people to connect to it. So what I'll do is I'll simply get off this machine for now. So Docker ps should not give me any output. All the containers are dead. So for running the container now again, I'll do one thing. I'll commit the changes whatever I have done to some image, and then I will be using that image to run the Docker container. Okay, so let's do one thing. The container name is Apache, so I'll create an image called Apache now. Docker commit, commit what? Commit Apache to what? To a new image called Ubuntu Apache. Okay, so if you check the layers, Docker history on Ubuntu Apache should give you one more extra layer on top of the previous four, right? So there are 5 layers this time. This is the fifth, and the previous 4 layers that we have downloaded. Okay, how do I start Apache? Make sure that Apache runs in the foreground, right, instead of a background. That's what is the prerequisite to keep the Docker running, Docker instance running. And moreover, we need to export the port. So I would say Docker run as a daemon and expose the port number 80 on the host and map it to port number 80 to the client. That means to the Docker container. Run it from the image called Ubuntu Apache that we have just committed. And the command for running Apache in foreground is user sbin Apache to CTL and run as daemon in foreground. Okay, that's the command from the Apache's documentation. It's nothing specific to Docker. I just want to run the command and make sure that Apache executes as a foreground daemon rather than as the background daemon. Perfect. So let's see if Docker container is still running. Docker PS should give us a container which is running, right? So a new name is given to it since we have not specified any name for ourselves. And if it is running on port number 80, which we have exported now on any of the IP address which are coming to it, it should be able to serve that request. Okay. So let me check the IP address of this machine. Here is the base machine, of course, 56.64. And if everything is running fine, we should be able to connect to the machine on port number 80. 56.64. So this default Apache Ubuntu page is being served from within your Docker container. It's not being served from the host machine. How do I prove it? Let's attach. So Docker attach to, okay, let me get the image ID first. Docker PS nostalgic Tesla. We'll be using this to attach. Docker attach to nostalgic Tesla. Get me the console. Oops, that's stuck. Never mind, we'll use another console for that. Docker PS. Okay, so Docker attach to nostalgic Tesla. Please do not block me this time. Still doesn't work. Okay, so let me do one thing. I'll close this sessions. We'll try to connect to it using some different command other than that. Sudo get the root. Docker. Docker has got another command called exec. So it runs a command in running container. So let's try it. Docker run, sorry, not run, exec, and I'm going to execute a terminal. I need a terminal in interactive mode. I want bin bash to be my terminal, and I want it on a container called nostalgic. What was the name again? Tesla, right? Nostalgic Tesla. There it is. So I've got a console, and to prove that this page is being served from within a container, I'll make changes to the index.html, which would be at var www html index.html. We'll say hello from Docker. Okay, so I've changed the content inside the file. Brilliant. So that's from within a Docker container. Okay, so whatever we have done with this Ubuntu image, if I want to automate that, am I able to do that? That would be the important thing, right? If we could even automate the creating of images, then that would be really nice. So let's create a small file. That file is called Docker. So I'll be creating a file called Dockerfile. The name of the file itself is Dockerfile. So I could write something like this: from Ubuntu latest. So that is my image name, and we are going to run the command called apt-get update and apt-get install y apache 2, right? That's what we did for installing Apache, and we want to expose the port number 80. I want to run the Apache as foreground, so I would be firing a command called user sbin apache 2. The next parameter that I want to pass to it is going to be -d, and the next parameter that I want to pass to it is foreground, right? Remember the command? So all these three commands, along with the properties that we have mentioned, should take care of themselves, and we should be able to uh, prepare a Docker instance all by ourselves. But this time we are not getting inside the container, we are not firing any of the commands there. So I'm going to save this and fire a command docker build. Requires one more argument, so you'll be taking it from the path. The path here is the current path, right? So it is building it up. Step 1, taking it up from the Ubuntu latest. Step 2, running apt-get update and installing Apache there. So everything is going to be automated using one single file. That the file name should be Dockerfile with D capital. So these Docker files we use in Jenkins. Jenkins would be firing the command docker build using the Docker file. So using that, the containers along with the code, along with the servers pre-deployed are created. Now these containers, when you run them again, you'd be having a web server running inside of it along with your code. So that's the fabulous part of it. No headache of managing the dependencies, no problems of environment replications, no problems about the configuration setup. You do it once, you replicate it as many times as you want. Okay, so that is all about Docker that I have to offer. Once this process finishes, we would be checking on the Apache server whether it is running properly or not. Okay, so it says successfully built, and the container ID it gave is B9888. Okay, no, it is 3832. So let's check Docker PS. Currently, we have got our own container running, so I would rather stop it. Docker stop the container FEF0BB. You don't need to type the complete ID even. It would automatically figure out which one you want to stop. Okay, Docker ps minus a. Which ones have I created? Uh, Docker images. Let me check. Right. So this is the one which is created now. And what I'm going to do is I'm going to run the Docker container from here. Docker run as a daemon this container, and don't care about the name. I want to fire a command which is going to be user spin apache 2 cdl minus d foreground, and the port that should be exposed minus p is 80:80. Working. Let's go back to the browser and check it. Nice. So this is the page that we have created from the Docker file. All right, everything automated. So that's all about Docker. If you have any queries or doubts, feel free to ask it. Any explanation that you need. Well, I need you to practice all these things again. If you find any thing which is complex, or any of the use cases that you are missing and not able to figure out where it has to be put in, or where it fits in the complete DevOps pipeline, you can always come back to me with the questions in the beginning of the class, or take them up at the end of the class. I wouldn't mind that. All right. So that's all about Docker from my side for today. In case you don't have any questions, we can drop off. So what's coming up next is second topic here in module 6. Um, we're going to cover a topic called Nagios, and in tomorrow's class, of course. And once we cover Nagios, we will see how to implement that using the client, on the clients, of course. So we would be monitoring the clients. We would be writing Nagios scripts for executing some custom checks that we would be building. Okay, so I'll show you a routine way of installing Nagios, plus a customized way of writing all the plugins and setting them up on the client side. So that would be coming up next in tomorrow and day after tomorrow's class. All right, so that's all from myself today. I'll beat you again tomorrow, same time. Have a great day ahead.